Hello everyone, my name is Cui Jin from StarFive Technology. Our topic today is enabling software emulation for RISC-V Heterogeneous core architecture. Before my topic starts, I'm glad to announce that StarFive's IP Jin is generally available to public from now on. It's a supreme 64-bit RISC-V CPU core independently developed by StarFive. It adopts deep out-of-order execution, superscalar, rich extension, and other design elements in microarchitecture, and has been highly optimized for performance and frequency. Its overall work efficiency will have excellent performance in data center, PCs, mobile terminals, high-performance network communication, machine learning, and other application fields. At present, Jin has been evaluated by company above applications, and its overall performance has gained client acceptance. Jin, as an important milestone in the development of StarFive's high-end processor core, is a representative RISC-V IP in the field of high-performance applications. For detail, please follow the StarFive website. So now we are back to today's talk agenda. At first, I introduce heterogeneous multi-core architecture scope we focus on. Second, this architecture will bring the software problems we try to solve. Then following that, the proof of concept of solution on QEMU is presented. At last, we summarize this talk. Why we need the heterogeneous multi-core processing? In a word, this is similar to the big and little arc in other SOC. That is a trade-off between performance and power. The RISC-V is an open source architecture, support many extensions in specs, and the SOC vendor has flexibility to choose a combination of different extensions to achieve better power, performance, and area. Thus, this is more challenging for its fragmentation issue in its ecosystem comparing with other closed source or license-based ISA. In today's presentation, we are focusing on the category highlighted in the right-hand side table. The big and little cores have the same ISA, but different extension, different microarchitecture for different performance and power, same memory view, and we want to run the symmetrical multiprocessing OS kernel on it. So the big core is a powerful core. That is introduced at the beginning, StarFive Jin. The little core we used is an in-order execution core with a different extension, such as we have no vector extension on it. In this case, we're facing a software challenge to solve the ISA incompatibility issue. Symmetrical multiprocessing OS require tasks can frequently, freely schedule on and migrate to any core seamlessly. But we will definitely meet the illegal instruction exceptions if we run the vector instruction on our little core. To solve this problem, we worked on a modified version of the QEMU to reflect such kinds of differences between the big core and the little core, and patch the Linux vector context switching to support any number of vector applications on such platform with affordable efforts. Now, I will hand over to my colleague Ley Foon to continue.
Before we have actual hardware ready, we can make use of QEMU to eliminate a heterogeneous multi-core system. It allows us to start some software development work or proof of concept work in the early phase. In the QEMU, we have a local patch to model 2 big cores and 2 little cores. Big cores are the vector extension and the 14-point extension of version 2.2. Little core are without vector extension and with different F extension version 2.0. After Linux is booted up on QEMU, as we can see from CPU info screenshot here, CPU 0 and CPU 1 are because the V extension, but CPU 2 and 3 are little cores without V extension. We have modified a Linux kernel to support heterogeneous multi-core system that we have modeled in the QEMU. Kernel needs to aware of CPU capability. First, kernel will pass the CPU ISA string for each CPU from the device tree to know the supported extension. With this information, we created a CPU vector capability list based on hard ID for each CPU. Besides that, we also need to disable vector optimized library in the kernel to avoid illegal instruction exception if it runs on a non-vector CPU. During runtime, context switching or signaling is based on the CPU vector capability. If it is a vector core, then the kernel will do the vector handling. For example, save and restore vector register. By doing this, we can run any number of vector threads on the big cores and support vector thread migration within the big cores. From the screenshot, we can see there are 3 threads running as highlighted in the color boxes. They run on the CPU 0 and CPU 1, which are big cores with the vector extension. These are 3 further possible software solutions here. The methodology is from compilation time to runtime, from static to dynamic. First solution is a compile time and loading time solution. A compiler can add the ISA extension information into application ELF section. Then the ELF loader assigns tasks to supported CPU based on this information. The second and the third solution are runtime and dynamic solution. It is transparent to user and compiler. Kernel can migrate tasks to support third CPU if encounter illegal instruction exception on non-supported CPU during runtime. The third solution is similar to second solution, but use software emulation to emulate unsupported instruction instead of migrating the task. Overall, each solution has its pros and cons, and their effort is from easy to difficult. In summary, we need more future work in hardware and also software to support heterogeneous multi-core system in the RISC-V architecture. StarFive will work with RISC-V community to drive this effort and anticipate contributing more to the community. That's all I was sharing today. Thank you.